Introducing WallEEG, a mind-controlled Quidditch robot. Here's what we want to do.
An interface that you can actually build on your phone so that we'd be able to control the drone from the phone. So then once we get a better understanding of the flight dynamics of the drone, then we can incorporate that into like some sort of EEG data. Okay, what does this person want to do? And then taking that and then actually making it do that thing.
Three, 2, 1, close your eyes. 3, 2, 1, open.
Here's a demonstration of the successful controls of the drone.
I got scared, man. I got scared. Up 1300. Alright, keep going. Yep, let's go. Okay. Alright, go then. Bye, Lily.
Here's the throwing mechanism that our team designed. We have built our own EEG headset for the biosignals board, which is also our submission for the fixed portion of the NTX SC20 challenge. Our headset is comfortable for wearers, modular, and easy to use for researchers.
This is our primary headset design. We came up with 3 primary criteria to work with: flexibility, modularity, and making it easy to use. As you can imagine, putting this all together into one design was actually more complicated than it sounds, because when you have additional flexibility, sometimes you lose out on how easy it is to use because of the complexity increases by a lot. That is why we came up with additional ways to solve this problem, and I will go through them as I explain the design itself. As you can see, there are 3 primary railings that go from the front to the back, and 1 main thicker headband that actually goes all the way across. Now, all of these have a tightening mechanism in the back so that you're able to press down as much as the sensor needs to get a more accurate reading, without hurting the user, of course. And you're also able to adjust this to different sized heads so that different people can use it and still get the same level of accuracy. Now, like I said, there's a lot of different moving parts on here, and it can become quite complex by the time that you realize that each of these things can move around. The headband can move up and down, these things move from side to side, and everything can get tighter or looser as necessary. To fix this, to help out with this, we created a code so that you're able to place this on, plug in the numbers to the code, and receive exact numbers on where to place the nodes. And as you can see here, there are measurements on each of these railings so that the user doesn't have to pull out a tape recorder or anything like that to actually measure out the head. Instead, you can just place it on, tighten the headband, get the measurement from the headband, plug it into the code, and the code will tell you exactly where to place all of the nodes.
After we had finished creating our design, we decided to compare it to previous year's design, to see the flaws in our design, or to see where we had improved from the previous years. Thankfully, we saw that most of our design had improved from the previous years. One aspect of it is how intuitive the design itself was. Our design is a lot more intuitive than our previous year's design because it works very much like a helmet. So users understand that it has to go on the head. And sure, there are some adjustments that has to be made, but our design is a lot more user-friendly as well. All you have to do is listen to what the program says and input the numbers it requires in order for you to be able to use the mechanism properly.
One of the cornerstones of our project was being able to distinguish between left and right motor imagery data and build a classifier out of that to use in our application. So to pre-process the data that we collected, the EEG data specifically from a teammate, we used the Z-score to standardize it and resampled signals at 256 Hz, as is pretty standard for EEG data. We then divided it into a training and test set and averaged and plotted it in order to get a sense of what our data looked like right here by each channel for each left or right motor imagery trial. Now, in order to extract useful features from this, we used bandpass filters, particularly in the frequency ranges we use for EEG, and then applied a common spatial pattern to each of the filtered signals. This gave us these plots, which kind of enabled us to determine which set of data, in terms of which band of data, was able to best distinguish between left and right motor imagery information. So that's what we selected in the feature selection process. We selected features from this particular band because it was easier to distinguish between those two sides of it. Now, to build the classifier, we used a support vector machine, which as a model builds a decision boundary between the data to split it into left or right. Now, in order to use this model, we gave it new EEG data in order to see whether it represented a thought of left or a thought of right, which we then sent on to our applications as a 0 or a 1 for left or right.
In light of the challenges posed by COVID-19, we were unable to finish building. However, we still wanted to demonstrate our technology with an alternative application, which turned out to be successful and also meaningful. So here's how we pivoted. Project Lumos is introducing EEG-controlled turn signals to the biking industry, increasing visibility and reducing risk for cyclists and cars. Downtown Toronto can have a lot of cyclists, and they need to communicate with the car drivers, which can be difficult in low lighting situations such as dawn and dusk, which are popular times for biking. And the current turn signal on bikes are, guess what, non-existent. So it's up to the rider to indicate what their next movements are, and they have to do so by raising their arms to indicate where they're going to turn. So if the driver fails to see that hand movement, then the consequences can be fatal. According to Canadian statistics, 7,500 cyclists are seriously injured every year from car accidents. To overcome this problem, Project Lumos is introducing EEG-controlled turn signals, which can broadcast the direction the cyclist would turn with the snap decision of the thought. This will allow the user to have much greater visibility on the road and more control, as you can always have both arms on the bike at all times. Project Lumos will attach bike signals in the form of arrows for clear identification to the rear seat of the bike, which provides a safer and a more alert turn system.
I'm Sonali and this is Jenny, and we're part of the NeurotechUofT team. Here we're demonstrating how a signal of 1 and a signal of 0 representing the thought of left or right, given as a result from our SVM model that's looking at EEG signals, can be sent to an Arduino connected to a circuit and demonstrating the left and right change on some blinkers. So here we're defining where the Arduino is located on a serial port. And in this for loop, we're just going to have a 0 and a 1 iteration, which will then first show 1 as a right being sent and then 0 as a left being sent. So I'm about to run that code and we can see what happens on the circuit that Jenny has. All right, so here we're starting up, and first we should see Python sending a signal of 1, which is correct, that is happening. And then the Arduino has received that signal of 1, which looking at this Arduino code, it's looking at the string received through the serial buffer. And then if it were to receive a left, it would switch to showing the left blinker, in which case we would know that the Python code has sent a left blinker, which is what we see right now. Going back to the Python code, we see that the Python code had indeed sent the 0 signal, which was received, and therefore the change happened. Thank you.